So it's the square root of the sum I and j of like lambda I AJI squared. I mean, that's...
Wouldn't it be the absolute value of the whole sum?
You might be right. Let me think about that. You're right. I should really write out that's the sum over j, the sum over I, right?
Oh, yeah.
So you're right. So the sum over I, fine. The absolute value. My bad. The absolute value of the, oh, good grief. I'll get it. Give me a second. The sum over j of the, yes, the absolute value of the sum of lambda I AJI, right, squared. Now we good? Does that make sense? So the jth component of the vector, the jth component of the vector is the sum over I of lambda I AJI, because that's the coefficient of EJ. So the definition of the complex n norm is I square the components in terms of their modulus squared, and I take the sum of all those and square root it. That's what I have now. See, this is the length of the jth component. I square it. I take the sum of all of those guys. I square root of that. That's the norm.
Oh, that is the norm.
That's the norm. And then the thing is, absolute value of x equals to 1 implies that the, absolute value, the modulus of lambda I is less than or equal to 1 for all I, right? So this, and that was a ji, my bad. So this is less than or equal to, the sum over j, sum over I of the absolute value of AJI squared. Square rooted. What I mean to say is that the thing inside the supremum is bounded by this. So, and that was the other. I think they're both true, but they are different estimates. I have used this in more than one time in my research. In places like it comes up. Okay, let me go on ahead here. So he then gives other examples. So I just think it's striking how much this resembles the Riesz thing. I don't know if you noticed it or not, right? I mean, it's very like, you see how it's similar? Like, what? What? Oh, it's all good. All right, so then he has a couple more examples, like the differentiation operator is an operator. If you integrate the integral operator defined by a kernel, cool operator, multiplication operator. Then he talks about.
Dr. Cook,
yeah.
I gotta go to practice.
Oh, okay.
Are you gonna go for like 30 more minutes?
I'll probably just be like 10 more minutes. They'll be done.
Okay, I'll watch it on YouTube.
Okay. See you later, Audric.
See you, Audric.
See you, Jacob.
Yeah. Talk to you later. Yeah. Bye.
Yep.
All right. So I wanted to make sure I wanted to contrast a couple things. Okay. So let's see here. I need to erase a lot of this. I just want to keep like one equation of all this and skip to something. All right. So essentially the neat formula we have here is among other things, it's essentially captured by this, right? T of x, comma EI is equal to, in his notation, the sum. I'll go back to my notation though, okay? J equals 1. Oh, stink. Sorry. J equals 1 to n of a I j lambda j, right? Where we'd set up x as we talked about before, right? Okay, so example, section 4.2, he gives some other examples as I was just talking about, which are interesting, like multiplication operator, how do we, the product of operators, he talks about the fact they could be anti-commuting. He gives the example of differentiation versus multiplication by x, and the fact that that doesn't commute. That's important to quantum mechanics. And he has a theorem that the product of bounded operators is bounded, right? The product of bounded operators is bounded. I'll write that down. So if you have bounded operators A and B and you compose them, all right, then that's less than or equal to the product of their norms. So here AB is the composition of operators, okay? That's how we multiply operators. And then this is all I wanted to get to today, so maybe it's not even 10 minutes, but theorem. So a bounded operator on a separable infinite dimensional Hilbert space can be represented by an infinite matrix. See, this is what I wanted to show today. I wanted to contrast these two theorems and also the Riesz thing, because the Riesz representation theorem essentially says a linear functional, right? Let me write it again up here just so we have it on the same board. It said what? It said f of x you can write as what? The inner product of x with some fixed representor, right? That was the Riesz representation theorem. This we just worked through for a linear transformation on complex n vectors. You can write its formula, right? And basically you can capture the formula with the inner product by a sum of numbers times the components. Right? So it's in the same family of thinking. It's not quite the same, but I don't know, when I read these things, to me it felt the same morally, in that weird sense of the word moral. So what does it mean, a separable infinite dimensional Hilbert space? What did that mean to us? What is separable? Oh yeah, a complete orthonormal system, right? Yeah. No, it's fine. It's fine. I've only erased things that we saw before, so it's all good. All right, so, but yeah, separable infinite dimensional Hilbert space meant that it had a orthonormal, basically an orthonormal basis in the extended sense of orthonormal basis, right? All right, so what do you think the formula is here? So this theorem, H is like, it's essentially the span of E1, E2, E3, and so forth and so on forever and ever, right? So X is equal to the sum I equals 1 to infinity of lambda I EI in this context, right? We trade our finite sums for infinite series in this infinite dimensional separable Hilbert space with our orthonormal system being, E1, E2, dot, dot, dot. And it is very cool. So if my bounded operator, I'm going to use T again. So here, what it works out to is T of x comma EI. Guess what it works out to? Well, it works out to exactly this, the sum of, j equals 1 to infinity of aij lambda j. And how did we define aij? Let's say T of EI is equal to the sum j equals 1 to infinity of a sub j I ej. So there's the ith column of the infinite standard matrix, which actually makes sense in this context. But this implicitly defines that. I mean, you could be more. I mean, if you want to, if you take the inner product of this with, with ek, then this all still makes sense. You can pull the series out because of the properties of the inner product in the separable Hilbert space. We've done some calculations like this before, and so you just get some. So this is like really a really nice place to be in, because while it's infinite dimensional, it resembles so much the finite dimensional context, like that. And of course that is Kronecker delta JK. That's what we meant by orthonormal system. And so out pops just a KI. So actually you could use this to define, if you wanted to. This might even be better. This defines the kith component of the infinite matrix. And it's infinite because k and I both range from 1 to infinity. So it's an infinite matrix.
But then those are infinite.
Yeah. Yeah. Which is a sequence that goes both ways, right? It's a sequence with two indices. They
Oh, yeah, okay.
this way and also that way. Yeah, I mean, it's big, but anyway, that's very cool that if you have a bounded operator on a separable infinite dimensional Hilbert space, it essentially resembles the same as a bounded operator. All operators are bounded on a finite dimensional space is the thing. So, but it is essentially the same thing, but I replaced the sum over n with the sum of infinity. It made me happy. Now, past this point, next time, hopefully I'll be more with it next class. We'll be doing bilinear functionals and quadratic forms, and I will try to cut through it. And I'm trying not to prove everything, but on the other hand, I'm trying not to sacrifice too many examples. I feel like I sacrificed too many examples today. The examples I didn't write on the board, it's just important to read over those because they're, those examples, well, you do some homework problems on them, you'll be fine, right? But anyway, I hope that suffices for today. Whew, goodness gracious. I think I've gone too long. Oh, yeah, I'm sorry.